A vertical plate is submerged in water. Express the force exerted on it due to water, in other words, the hydrostatic force on it, as an integral. So we will look at different parts having different shapes submerged in water. Again, the thing that's different about this is that it's vertically submerged in water. If it was a horizontal plate, it would be much easier. We would just do rho g dA and be done with it. But because this is vertical and pressure changes as we go up and down, then we have to do the integral analysis. So, as we said earlier, set up an axis first. So this is 4 feet, this side is 3 feet, and it's 1 foot below the water. I'm going to choose my axis to be at the surface of the water. Again, it doesn't have to be like this. I'm just going to choose it like that. Maybe we'll look at it both ways and show that it's the same result. So I set up my axes. I chose the top of the water to be the x-axis, and then I'm choosing the downward orientation to be positive. So this corner right here is my origin for me based on my axis. That's step 1. Step 2 is to analyze rho g dA. Again, if it was a horizontal plate, all you would need is the distance and the area of the plate, but because things are changing here, I'm going to pull out the rho g outside of the integral, figure out my d, figure out my a, figure out this guy, and see what happens. So let's say I take one representation, one slice somewhere on that vertical plate, and I'm trying to find out how deep it is below the water first, because I want to figure out what d is here. And so there is d, how far below the water that representation is. And if I take that back to my origin, that's just a vertical distance touching the origin. So it's just a segment y, nothing more than just a y value. Again, I repeat, if that piece was lower, it would be a longer y value. If that piece was higher, that representation was higher, it would be a shorter y value. Nevertheless, it's a distance y. So we found our distance below the surface of water. For the area of that piece, I have to do length times width. It's roughly a rectangular region, and since this I call the y-axis, what the width of that thing is a delta y. So I have my width, delta y high, which I'm just going to put as a dy in my integral. So I have my width to be dy or delta y, and I need to figure out what my length is. And I better figure out that length in terms of y values because I'm doing an integral with only y's. And I have a triangular shape, so very likely I'm going to use similar triangles for this one because that just seems to be the easy way to go. So I'm going to take that triangle out along with the length that I'm interested in so I can put it in terms of y's. Now this top part was 4 feet, this side was 3 feet. L is the guy I'm looking for. I want it in terms of y's. So if I'm going to do similar triangles, I'm going to do 4:3, let's say, as L is to this guy right here. So in order for me to figure out what this guy is in terms of y's in my picture, let's go see what that looks like here. This is the guy I'm interested in. Now keep in mind, if that's the origin 0, 0, and this is 1 foot below, and I have another 3 feet, down here, I must have y equals 4. Let's also label this as y equals 1. So if I'm interested in this little bold red section that I want to figure out, well, that's dangling up on the y-axis, and it's dangling up on the y-axis, and I very well know what this is. Remember that blue d distance that we called y? If I know that that's y, and I know that the whole thing is 4, well then this must be the leftover. It looks like this piece is just 4 minus y. Again, the whole distance all the way to the bottom is 4 units for y. This blue segment that I already used was just y. So the leftover is 4 minus y. And I'm pretty much there. I'm going to cross multiply and get what L should be. And it looks like L is equal to 4/3 4 minus y. So we got our length in terms of y as we had intended. So I'm going to go put that here. 4/3 4 minus y is my length. I have my distance, I have my length and width. The last thing I need to figure out is from where to where in my picture am I making up the slices. Well, the slices start from here and go all the way to down here, and based on my axes, those y values are from 1 to 4. And since we are dealing with feet, we're in the US system, so this guy over here is going to be 62.5 from 1 to 4 y times this business dy. And that's all we had to do. We just had to set up the integral for the force. Now, of course, if I want to find the value of this force, I can use my ti because that's just a polynomial. We all know how to integrate a polynomial. So let's go actually calculate the force as well. So I pulled out the 4/3 as a constant, and I will just punch this guy into my ti and see what it gives me, then I'll multiply it by these guys. So math, then push 9, x times 4 minus x in terms of x from 1 to 4, push enter. That guy times 62.5 and that guy times 4/3. And it looks like we get the force to be 750 pounds. Remember, we're in the US system with feet, so the unit for force is pounds. Now, we could have set that up a different way with a different axis, even used the equation of a line to figure out the relationship between x and y, but it was just ready to go using similar triangles and made it easiest. Let's look at another problem. Okay, same question. Find the hydrostatic force on this vertical plate submerged in water. So basically I just need to worry about force acting on this piece because the other part is not submerged in water. First thing, remember, is set up an axis. After your axis, you got to do your rho g dA business. So due to symmetry of this problem, I think it'll probably be best if we set the axes right smack in the middle. And again, I like putting my axis at the top, the surface of the water. So this will sort of be like my origin, my 0, 0 spot. And the downwards direction I'll just keep positive to make things easy. So the shape looks a little bit different, but it's okay. We'll just go figure out a relationship between the variables we're dealing with. I'll call this guy x again, and I'll call that y again. I'll make one slice and then just focus on the d and the a on that slice. So that representation that I've made is d units below the water. And again, if I take that segment and push it back to my origin, that's just the vertical distance touching the origin, which is exactly y, the same as before. So the distance below the water is y. If you make your axis be at the surface of the water, you notice that your distance will always be y. It just depends on which way the picture might be easier. I like usually putting him at the surface of the water. Alright, now for the area, I gotta do my length and width for this guy. And again, my width is a little delta y, so I'll put it as dy in my integral. And I just gotta go worry about the length. So I want to find this length, and to make things more accurate in my integral, the length actually of my entire segment, remember, is not just L, it's 2L. So for the area, I really, based on my picture, I'm going to say it's 2L. That whole length is twice what I'm in search of finding based on my picture. So you can call that something else and then double it and put it for your L, or I'm just going to go ahead and say I'm going to find L and then double it to put it in there and get a 2L. So now analyzing this might be a little bit harder because I don't have a triangle right off the bat. So there are different ways to do it, but what I could, I guess, do is make my own triangle. What if I did that? If I did that, I know this distance right here is going to be 1 meter for sure, right? Because this whole bottom is 2 meters, and I've cut it smack in the middle, so that distance is going to be 1 meter. I just need to find this guy and add it to the 1 meter, and I think I'm going to be good to go. And you need to find everything in terms of y's, it looks like. So basically L is going to be, L will really be that 1 meter that I'm sure of, plus that little segment, which I'm, I guess, going to go ahead and call Z. Now there are other ways to do it and maybe come up with the relationship between X and Y, but that's the first thing I saw, so I'm just going to go about it and do it that way. So it's going to be 1 plus Z. And then to find Z, I can use these similar triangles business and then plug it in accordingly. So if I were to zoom in my camera on here, it would be basically this piece I'm looking at. Some of it is fixed at 1 meter, and then Z is the little piece I'm focusing on. And I guess while I'm at it, I'm going to take this portion out, sort of zoom in on it, and maybe not even that. Let's think of it like this. That might be easier. If I think of this triangle, I have a Z that I'm looking for, and I actually know how long this is. This whole thing is 2 units because I have 1 meter and 1 meter making 2 units. So for the big triangle, I have a 2 here. And then for this piece, I guess, has to be 1. Because if this is, whole thing is 4, and the middle portion is taken up by 2 meters, that leaves 1 meter here and 1 meter there. So my big triangle that I'm focusing on is 1 and 2, and then Z is the guy I'm looking for in terms of Y. So I have to figure out what this business is to make up my similar triangles. And that in my picture is right here. That's the little distance I'm interested in. So if I take that segment back into my axis, notice that's dangling up in the air away from the origin. We do know that this whole region is 1 meter. So this is, I guess, y equals 0, and at the bottom it's y equals 1. So if I'm interested in this little thing for my picture, and that's dangling up in the air away from the origin, and the whole thing is 1, and that blue portion was D, or Y, that we found, then I guess the leftover for the little red segment has to be 1 minus Y. So this guy is 1 minus Y based on my picture. Well, so let's go ahead and do our similar triangles. 1 is to 2. 1 is to 2 as Z is to this distance. Let's cross multiply. 1 minus Y is equal to 2Z, and I guess Z is 1 minus Y over 2. So let's go back up here. L is 1 plus this business, I guess a half of 1 minus Y for the Z value. And I'm going to have to double it to put it in there. 2 times all that business, 1 plus a half, 1 minus Y. So since I'm in the metric unit system, I'm going to put 9800 for my rho G. I have my Y. Let's distribute this guy in. I have 2 plus 2 times a half is gone, 1 minus Y, and then my dy. And let's go back and see where we're making these vertical blue slices. The vertical blue slices are going on from 0 to 1, it looks like. So let's clean it up a little bit, combine like terms, 3 minus Y, and we're ready to punch that into our TI and see what we get for the force. So with the TI, again, it's just a polynomial. We can quickly distribute that and integrate it by hand, but we'll use our TI. So math 9, x or y times 3 minus x in terms of x from 0 to 1. Let's push enter. And then multiply that guy by 9800. And we get approximately 11,433 newtons, again because we were in the metric system. So the key is, again, to set up an axis and then look at your picture and figure out the 4 components of your rho G dA business. We'll look at more examples in the next video.